So, okay, now let's look at this set of companies. So we have here a bunch of major tech companies. What do they all have in common? They have top-notch security teams, good security records, but they've all actually had their users attacked via issues with their software updater. Okay, and if these companies can get this wrong and have problems, then this is something that I'm sure should scare everyone in this room. All right, and we'll talk a little bit about why that is in the case. So first of all, I think it's obvious that updates are inevitable. You're going to have to update software at some point. And let's think about cars for just a minute to make this more concrete. Lots of code. You'll have regulations that might change, that might require things to change, and so on and so forth. And in the past, in the automotive case, recalls are extremely expensive. If you have to actually take devices in or pull in hardware, pull things back, that's just so cost prohibitive. So in practice, you need some way to update things in the field, as I think everybody should realize now. And updates are actually, like, the ability to do an update to a device is like the key thing to do to take control of a device. Because when you think about it, you think about all the attacks that you might have learned about, when you took a security class or just reading about online. You hear about, buffer overflows and use after free and ROP and all these like advanced, attacks that people are coming out with. What are those all about? It's about the attacker wanting to make your computer do something that they tell it to rather than what it was programmed to do. But if I can just push a software update to you that you think is valid, that has my code in it, then I've won. I have everything, right? So like this is the holy grail for hackers, is to be able to do software updates on a device, okay? And nation state actors use this holy grail repeatedly. So, when allegedly the United States and allegedly Israel wanted to go after centrifuges in Iran to shut down their nuclear program, they built two pieces of malware, Stuxnet and Flame. And the much more advanced piece of malware was the Flame malware, which was on the more traditional PCs rather than the embedded systems. And this spread through Windows Update in order to go and do this, spread through two flaws in Windows Update. And when North Korea allegedly wanted to attack South Korea, back when there was the whole, anyway, it doesn't matter. But they've had a lot of disagreements over time. But back in one of their disagreements, they used a mechanism in software updates and like configuration management to cause about $750 million in damage to their system. And also, of course, we have the NotPetya example, which was allegedly Russia going after Ukraine to talk about software updates. So one thing to worry about with a lot of this is nation state actors pull off extremely complex attacks, okay? We'll talk a little bit, I'll talk a little bit about the SolarWinds hack that happened, but it was not something that, just 14-year-old boy who happens to plug into a network and is interested in whatever is going to be interested in trains is going to be able to pull off. It was a smart, well-resourced attack. And so you need to design systems that assume that attackers are going to be successful in some parts of what they're attacking. So what kind of things do you have to worry about in order to do this? So I'm not actually going to go through these, so you don't need to read this, but this is just meant to show you there are long lists of types of attacks that you need to be concerned about to build and design a system to do this securely. It is not something where you sit down and think for an afternoon and come up with a solution, okay? So you need to be concerned about many things. So let's see how people try to prevent these attacks. And first, we're going to look at some examples of what does not work, okay? And these are basically the designs of the companies whose logos were on the slides before. In most cases, in many cases, the designs they were using 5-6 years ago, and many of them have moved to TUF or other designs we're going to be talking about later on. Okay, so traditional solution one is, hey, I'm just going to use TLS. So there's just going to be some key on the repository, and then what's going to happen is there's some way that I tie this this key to the repository either through the traditional CA system, or I bake the public key into the devices that I put out so that they know where to get the update from. Okay, so what do we really need? Okay, we want a design that lets us survive a compromise of the server, compromise of keys, compromise of things that could reasonably be compromised with the minimum possible damage. So we want to be able to minimize the damage of a single key being exposed, be able to revoke keys. This is really important because if you don't have a way to go from a compromise back to a secure state, you're in a lot of trouble, right? And you have to prevent a bunch of other things here. So I first got started in this space, as I said, a long time ago. I was just starting my dissertation work, and I designed the first package manager used for what we now call the cloud. And I found, in this process, I found serious security problems in the design, not the implementation, but the security design of the way that the 10 most popular package managers all did their signing and verification of packages. So, and I showed that I could compromise millions of devices, and I worked with the distributions to upstream this. And then I wrote a paper about it, because being a naive young academic at that point, I thought writing a paper and even upstreaming things, even like working with people, that means I've done my job. This problem will be solved for all time. I'll never have to work on software updates again. Then some folks from the Tor project came and said, hey, we read your paper. We really liked it. Can we come visit you in your lab and spend some time and you look at our updater and help us design a better one? And they said, how hard can this be? So they came by for, a couple of folks from the Tor project came by for 3 days or so. And so then they went and came up with, they said, we know we don't use TLS, so we can add signatures this way, but then you have a problem with replay attacks, and if you do this, and you have a problem with freeze attacks, and so on. So we worked through this over a period of 3 days, worked through a lot of the parameters with them, and then they went away. And they said, hey, we have this thing called Thandy, this awesome software updater for Tor. It uses a few different things here based on what we discussed. And we want you to review this and just take a quick look at it before we go live with it. And so we did, and we found 8 serious security problems in this, including 3 that would let any man in the middle root all users of Tor. Okay? And at that point, it really sunk into me that it wasn't the kind of thing where we could tell people how to build a secure updater and it would happen. We had to sort of provide it for them and provide them a library and mechanism to do that. And at that point, we started the Tough project, where Tough is meant to be something that you can drop in and use as an updater that provides you with this compromise resilience. It secures software updates. It assumes from a very serious threat model. It assumes that your servers will be compromised, your network could be completely compromised, keys can be stolen or used by attackers, and Tough tries to minimize the impact of this so that if and when these things happen, you don't end up having your users have rooted copies of things all installed. And importantly, this isn't some crazy blue sky academic thing where you have to change the entire world in order to make it happen. It layers well into existing systems. So Tough's design is based on 4 different key principles here. The first is, and I'm just going to talk through these at kind of a high level just so you have some idea about how this works. So the first is responsibility separation. So the idea here is that rather than have one key that's responsible for all the types of things you might want to do, such as being able to say, this is an authentic package, or this is the latest package, or this is the correct key to trust for to use for this specific role. We split those apart. And so the example I just gave here is a key that's saying this is a correct version of this package is different than the key that's used to say there has not been an update in the last 10 minutes or something like it. Because this key, as we'll see, if you're trying to say repeatedly there hasn't been an update recently, there hasn't been an update, oh, now there's an update, you need to use that key all the time. But when it comes to actually signing and pushing a new release, you maybe only do that, depending on your model, you maybe do that daily, or you maybe do that, infrequently, like on average once a week or something like that. So those keys can be managed differently. Another idea here is that you minimize the key and roll risk, so that because the expected damage you're going to have is roughly about equal to the probability of that happening with the impact. So if you have a roll that's a really important roll, then you need to have it be very unlikely that this is going to be compromised. So in our system for root of trust, what typically happens in most of our deployments is that different people at that organization have keys in like YubiKeys or something like it that they keep in safety deposit boxes in different areas. And some group of them may have to come together in order to do something like deal with a really catastrophic compromise. But that also means that if an attacker wants to compromise this role, they have to pull off like a Mission Impossible style heist where they simultaneously get into lockboxes at a bunch of different places and are able to get key material. Whereas if you have a role that needs to be used, online all the time, you want the impact of that role being compromised being very low. So if like this timeliness key, if the key that deals with that is compromised, then you can lie for a short period of time and say, hey, there hasn't actually been an update, in the last few days when maybe there has been one. But the actual impact of this is very minimal for your users. They might be, a day or so behind. Okay, another thing that Tough supports is multi-signature trust, where this is like the two men in the submarine who have to turn the keys at the same time to launch the nuclear weapons. You can do this and say, in order to release something, both a person from our development team and a person from our QA team have to both approve it, for instance, or do other things like that in order to make things be considered valid. Yeah, and I already kind of said that. And so if one of those keys is compromised or you have a problem, it's not a real issue. And the last is, Tough is really unique when it comes to most like popular deployed security systems. Anybody who's had to deal with like revocation for X509 in the whole CA system we have now knows that that's just a disaster. Like it just does not work well. Anybody who's had to deal with revocation in GPG or PGP, it is horrible. It's a mess. And if you have an example of a system that does revocation well, please tell me. Right? I literally, like I've had people ask me, like, what's an example besides Tough that you think really does this well? And I sometimes ask the audience, and I've never had somebody really volunteer one and be strong about it. The reason why I think we ended up doing this right is not because we're more clever or anything like that, but at the very beginning, this was a primary goal of Tough. Because if you want to recover from, be resilient to compromise, you have to recover securely. And because this was always a goal from the very beginning, it wasn't something that got done in the 1.1 release or 1.2 release bolted on, it's so fundamental. So we do explicit revocation where you can say explicitly, like, this should no longer be trusted. Tough also has this notion of implicit revocation where after a certain time, this thing should no longer be trusted. And these mechanisms are both really important for security in practical situations. Okay, Tough is widely used in industry by all kinds of prestigious companies and organizations here. It's a Linux Foundation project at the highest level, the Linux Foundation inside the Cloud Native Computing Foundation. And yes, we're very happy with all the support that the CNCF and Linux Foundation have given us. So now I'm going to talk a little bit about automobiles, which present a whole bunch of unique problems. Because they may have 30, 40, 50, even as many as 100 different computers in them that need to be updated and have very limited connectivity and so on. So back in 2015, maybe a little earlier than that, someone from the Department of Homeland Security reached out to me and said, hey, there's a problem. The automakers need a way to secure their secure updates to their vehicles. Would you be interested in doing this? And I was like, yes, this is great. And started work along with a couple of other researchers at groups at the University of Michigan and Southwest Research Institute on building this as kind of a industry, government, academia collaborative project. And so we built something called Uptane, which is, you can think of it kind of as the automotive variant of Tough, but it's really more of a variant of Tough that works well on more embedded, closer to embedded devices. So it's probably 99% of what you need for almost all IoT situations. And I'll talk about what to do about that other 1% later in the talk. But it has a couple of interesting things that we didn't use in Tough because of the way that Tough works and the threat domain and other things like that we had to build on top of it, that I'll talk briefly about some of these in a moment here. So as before, Uptane's goals are to prevent attacks, have compromised resilience, and minimize damage. So basically the same sort of stuff as Tough, only applied to an automotive domain. So one natural thing that you need to think about and worry about is the OEM will need to do things like tell an ECU which images it needs to be installed. And so the way to think about it is your campaign management, your choice of what to install in a vehicle, is also if you keep the keys online that say what things are authentic and use that for campaign management, then you have a real problem because a repository hack will compromise all your users. If you keep your campaign management keys offline, you can't, right? Because you have to use them all the time for your campaign management, right? Does that make sense to everybody? So one of the innovations we sort of had here was a way to combine it so that you can have one repo that basically says this is the set of valid images that any campaign might use. And then you have another repo that says, okay, we are pushing this campaign out to this specific vehicle, right? So image repository is the valid list here, and let me go through director. Okay, and then what you do is a vehicle will go and get the list of valid things from an image repo, and then be told which things of that list it should get from the director, and then do the installation inside the vehicle. The primary ECU is something like your telematics unit or some other powerful unit in your car that has an outward network connection, and then it can go and push those updates to the individual ECUs that are in the car, some of which have more computing power and some of which have less. So I hope that general idea makes sense. And so the basic timeline for this is that we got the initial grants and then started to work with a few other organizations to really build this kind of industry, government. We had regulators and everybody in there from organizations around the world from the very beginning. We then started holding workshops. We standardized it under IEEE ISTO, and officially joined the Linux Foundation under the JDF, released a standard under the Linux Foundation, and have gone and continued to push and promote standards. We're on standard 2.0 of this now. And one thing I want to say about this is, it might be scary to some people to hear that we started at, we had our 1.0 in 2019, and it's 2022, and we have a 2.0. Okay? Because that seems like it's moving kind of fast. Well, really the only differences that we've had from the 1.0 until now, from a code standpoint, are almost zero. If you take a 1.0 implementation, the actual changes you need to make it 2.0 are effectively zero in most cases. The things that we've done, though, is sometimes we've taken a must and made it a should, or added clarification around some of the text or other things like that. And some of the musts to shoulds force things like us to bump the major revision number, should to must to should. So it's constantly worked on, but like all of the work here is basically copy editing work to make it read more like a better formal standards document than any actual changes to the system. We also have a deployment best practices guide that we've released for it, and yeah, has been contributed to by a lot of different folks, even though the automotive industry is very, very shy about anybody doing anything publicly. We yeah, have done a bunch of outreach with it as well. There are a bunch of white papers, tutorials, other things like this in a variety of formats and languages and things like that about how to use it. Uptane, more recently, we have been supporting, doing work to support better integration into earlier stages of the software supply chain. So if you have compromises, these are less problematic for you. And I'm going to be talking a bit about that. There are also a bunch of different implementations of Uptane, including the excellent Actualizer implementation, which is an open source implementation used in a few different places, including automotive grade Linux and also the Torizon product. We also have workshops all around the world if you're interested in joining or knowing more. So I'm just going to wrap up this part that I've talked about so far about Tough and Uptane. I think that these projects have been successful in part because we worked a lot with industry, we worked a lot with government, regulators, and other people like this. And we have an open design. Everything, by the way, everything that I've done and everything I plan to ever do in the future will be open and free for anybody to use for any purpose. Open source, open design, etc. And this is really beneficial because it makes it free to experiment with and use. It's easy for end users, easy for adopters, and so on. And also, when something does happen, when there's an incident in the news, and I'm like, hey, I went to this company, I told them there was a free solution available, it's been heavily audited, it's the best standard, and why they didn't use it, we don't know, but now their users are paying the price. It feels a little different than me saying I tried to sell them my product, but they didn't buy it.